What you're hearing is Hardie fiber cement siding living up to its reputation as the siding that helps resist weather damage, no matter what Mother Nature throws its way. James Hardie knows how important a reputation is, especially when you're a home builder. That's why Hardie products withstand the elements better than wood-based siding, with styles to match their strength. Because when home builders work with us, we deliver our best so they can look their best. Protect your reputation with exterior products by James Hardie.
Hi there, Andrew Dunkley here, and you're listening to Space Nuts Q&A edition. Glad to have your company once again. On this episode, we will be answering an array of questions on very different topics. Jake is asking us about tidal lock. That's not something to hold back the water in the Thames River. No, something completely different. Clint wants to talk about the heat of the sun. Emily, Sandy's daughter in Melbourne, wants to get to the moon, and we're going to tell her how. And Fenton has asked a vast array of questions which could probably fill an episode on their own about the radiation of Jupiter. That's all coming up on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9, ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining me once again is not Professor Fred Watson, because he is overseas looking at the sky up in the Northern Hemisphere. But with us is Professor Jonti Horner, Professor of Astrophysics at the University of Southern Queensland. Jonti, hello.
Hey, how are you going?
I am well. We're working on getting you your own intro, but we're in a time of year where all the radio stations in Australia want new jingles, and our studio producer who does all that work is flat out at the moment. So we've been put on the back burner, I think. But you can understand why all the radio stations want to ramp up how they sound so that they can get new audience. I worked in radio for 40 years. I'm pretty sure changing a jingle doesn't actually do much. But just my observation in 40 years.
We'll probably get it through just in time for Fred to get back.
Yes. I think that's exactly what I was about to say. You stole my joke. Never mind. But what we'll do right now is look at some audience questions. I love this particular episode every week because it's the audience's chance to get involved. And we've got a few audio questions coming up. But our first one comes from Jake, who actually sent this question via Facebook Messenger, which we don't often catch because we don't monitor it as much as we probably should, but we just haven't got the person power. But I just happened to be sort of on my iPad the other day and went, oh, hang on a minute, there's a little one there. Greetings from Tennessee, USA. It's Tennessee, home of the Titans. I know that several two-body systems are in various stages of tidal locking. I was wondering if a star or planet with several orbiting bodies can even become tidally locked with a particular one. For example, can the sun become tidally locked to one of our planets? Likewise, can Jupiter become tidally locked to one of its moons? I assume that if such tidal lock can occur, the larger body becomes locked with its most gravitationally attractive orbiting body. But if that's the case, how are the other orbiting bodies affected? Love the show. And that was a question from Jake Tyler. I got a feeling that he's going to, some of the things he said in the question are the reality.
Yes. So there's a lot of complexity to this. It's a really, really good question. Now, we're familiar with tidal locking anytime we look up at the annoying source of light pollution in our sky that is the moon. You know, it keeps one face pointed towards us all the time with a little bit of rock and roll because it's being nudged by everything else. It's not on a perfectly circular orbit. But it essentially keeps the near side of the moon faces towards us, the far side faces away. It rotates once on its axis in exactly the same time it takes to go around the Earth, essentially. So it's turning as it goes. The Earth is slowing down in its rotation as the moon is getting nudged away. There's this tidal interaction between them that I always visualize essentially as being the result of the tidal bulges the moon raises on the Earth. So we get high tide and low tide every day. Yeah. And I view those a bit like brake blocks on a wheel. They're kind of applying friction to the Earth because the Earth is turning under them once every 24 hours or so. But those tidal bulges are doing one lap every 27, 28 days because they are tied to the location of the moon and the sun. So those bulges are dragged along by the friction of the Earth. They're pulled slightly away from that line between the moon and the sun, which means that they are then pulling a little bit on the moon and causing the moon to speed up, which means it moves away. So you've got this transfer of energy and momentum between the rotation of the Earth and the orbit of the moon. So the Earth's spin is slowing down and the moon is moving further away. Now, in theory, if we could carry on for long enough, that would eventually slow the Earth's rotation down such that it matched the orbital period of the moon. There is some debate, though. That will not happen quick enough for it to happen within the age of the solar system that's left. But there's also some debate as to whether that would happen before the moon gets far enough away to escape the Earth's gravity. So in the case of the Earth-Moon system, it's not going to happen, but it illustrates that it could. So we'll move out further out in the solar system to Pluto, the dwarf planet. And we talked about Pluto a couple of weeks ago having this big companion called Charon. Yeah, Pluto actually, though, has about 5 moons. It's got Charon, which is huge, and then it's got 4 little ones in Kerberos, Nix, Styx, and Hydra, I think they're called. And then smaller ones further out. Now, Pluto and Charon are tidally locked. Charon spins once in the time it takes to orbit the center of mass between Pluto and Charon once. So it always keeps the same side facing towards Pluto in just the same way that the moon does going around the Earth. But Pluto has also tidally locked with Charon. So Pluto keeps the same face pointing towards Charon all the time. So that's a prime example of the kind of system Jake was asking about. A case where the biggest body has locked to the second biggest body, and they're both locked together, and there are other things in the system. When it comes to planetary systems, and when it comes to the more generality of it, it gets a bit more complicated. So there's a few things going on. It's not necessarily the most massive body going around a star that would be the one that it tidally locked to, because the distance is important as well. And tidal forces fall off incredibly rapidly as a function of distance, much more quickly than the r-squared fall off of the gravitational attraction. I think it's either an r cubed or an r to the power 4 setup, which means that the closer you get to the star, the much more strongly you tidally interact. Now, we see this with exoplanets. We can see that exoplanets that are very close to their stars are tidally locked. The ones that are further away are probably not. But we also see it in the form of tidal circularization of orbits. So you get a planet that is flung onto an elongated orbit where the closest point to the star is very near the star. Because of the degree to which tidal forces vary as a function of distance, that means the star will interact much more strongly with the planet in a tidal sense when it's near the closest approach than when it's far away. That means that you will get, you'll get an attempt to tidally lock the planet. So the planet's rotation will be getting merged into a rotation period that matches the orbital period. But at the same time, you get this dissipation of energy that tries to make the orbit more circular. And that dissipation of energy is happening at the periaps of the orbit, the point in the orbit where it's closest to the star. So the result of this is that that orbit gets more and more circular by bringing the apoaps, the furthest point from the star, closer to the star. So it ends up being circularized at that closest approach distance. And that happens more quickly than the tidal locking process. And that's the result of the fact that the tidal forces fall off much more strongly as a function of distance. We haven't yet found any stars that we think are definitely tidally locked to their planet. Now, part of this is down to the mass difference. So the small thing will tidally lock much more quickly than its bigger companion. That's what we're seeing with the Earth and the Moon. Yeah. But it's not beyond the bounds of possibility. And there are suggestions that tidal interactions between really massive planets, planets a lot bigger than Jupiter, and stars, when the planets are really close in, can have a significant impact on the spin of those stars and also the energy dynamics of what's going on in their interiors. Not totally my area of expertise, I've got to flag that. But this is something that people are having to think about when they come to looking at ways of measuring the age of stars. Now, there's a few ways you can do this. I've got colleagues at UniSQ who work on asteroseismology. They're looking at how stars wobble and wibble, ringing like bells that have been struck. And you can look at the different frequencies at which they're wobbling and wibbling to learn a lot about their interior. And that kind of study can give you an estimate of the ages that's really quite accurate. But it's really resource intensive. You need to stare at a star for a long time doing a lot of observations. If you're trying to just get the age of stars in general, there's a technique called gyrochronology, which is essentially measuring the rotation speed of the star and using that to get a first estimate of its age, which will have quite big uncertainties, but seems to do a reasonably good job. And the idea here is that when stars are born, they're born from material collapsing in, which spins faster and faster. So typically a newly born star will spin quite quickly every day or two. But over billions of years, all the mass it's losing through the stellar wind will kind of act as a brake on the star's rotation, taking away that angular momentum, causing its spin to slow down over time. So if you know the degree to which stars slow down as a function of time, and you measure how quick a star's spinning, it gives you an estimate of its age, because an old star will spin slower than a young star. But if that star's got a really close-in planet that's interfering with it tidally, that'll impact that process.
Yeah.
So there's a lot of aspects to this. I appreciate I'm going a little bit off topic from Jake's question, but it shows you the complexity of it, and it's why it's such a good question, because it's something that we don't know the final answer to, because it's going to depend very much on each individual system. For the Earth and the Moon, we're probably never going to get fully tidally locked to the Moon, but we know that when the dinosaurs walked the Earth was spinning quicker. And we've had independent verification of that. Not only do we know that from the tidal motion of the Moon moving away, we can measure the speed the Moon's moving away, but there are also measurements that have been made of fossil beds that show that there were about 380, 390 days a year back in the Cretaceous. Now, the Earth's orbital period hasn't changed, as measured in the number of seconds. So how do you get more days in a year? You get more days in a year by making the days shorter. So that's the direct outcome of that tidal reaction between the Earth and the Moon. Pluto is a stage further along. That's fully locked up. You've got an interesting case in our solar system of Mercury, which is trapped in a 3-2 spin orbit resonance. So it's tidally locked, but it's not locked in 1-1. And the only reason that works is that Mercury is on an elongated orbit and is also not a perfectly spherical object. It gets quite complicated.
Yeah.
But this gets odder the more you study it, basically, and there's a lot of depth to it. So it makes it a fabulous question.
Yeah, certainly is. Thank you, Jake. A question popped into my head while you were talking. You talk about the effect of the Moon on Earth's oceans, the tides. Would it be too extreme a thought to suggest that the tides are actually just a slow motion tidal wave?
You could possibly think of it that way. I never have done before, but it's an interesting one because the phrase tidal wave in itself is quite misleading because they're not really waves in the same sense as the waves we see on the beach. So this is where when you see disaster movies and you get this enormous tall breaking wave, that's not really what a tidal wave's like. A tidal wave is a huge body of water rising and falling. So it's more like the surface of the ocean getting higher or lower. Yeah. And it's only when it gets really close to the coast that can break. So I know people who are into geophysics and ocean dynamics who get grumpy at disaster movies for getting tidal waves totally wrong. But in that sense, our tides are very much like that. It's the same kind of process, the water rising and falling. And a huge body of water doing that means it sloshes around a bit as well. A very similar thing. And tied into this, of course, when the Moon was closer to us, which it had to be in the past, when the days were shorter, the tides were higher and more extreme. And that's tied into arguments people have had about the origin of life, suggesting that the origin of life happened in the intertidal region on the coast, which would have been larger when the tides were higher, but the tides were happening more quickly as well. So the inundation and drying out happened on a quicker timescale. So that's down to the Moon.
Yeah, it's intriguing. It's amazing science. Thank you again, Jake. Great question. Glad I happened across it the other day. This is Space Nuts. Andrew Dunkley here with Professor Jonti Horner.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Let's go to our next question, which comes from Clint.
Hi, Fred. Hi, Andrew. This is Clint from Rome, Georgia, USA. Love the show. Happy New Year. My question, though, comes from the sun. We know the surface of the sun is around 6,000 degrees Celsius, but the corona is much hotter, millions of degrees. I know scientists are still puzzled with this phenomenon, but my question is, could this be due to the gravitational pullback towards the sun that is causing some kind of friction on leaving matter that the sun is losing or projecting? just a thought I had when reading how the Parker Solar Probe came its closest to the sun earlier last year or this year, depending on when you're listening to this. And they use its own gravity to power it quickly through the surface of that corona. Just a quick question I had while exploring that. Thank you.
Okay. Thanks, Clint. Love the accent. Now, I know the sun isn't your main area, but I'm guessing you've done your homework on this question.
A little bit. It's actually a real head scratcher because it's pushing the boundaries of what we know, and that's what I really love. So, the first thing for me to say here, and I think it's always important to acknowledge this, is that I don't know the answer here fully. I'm not an expert, but part of the beauty of science is asking questions we don't know the answer to. That's what makes a scientist. If we already knew the answer to everything, it'd be really, really boring. And the sun's corona, and by extension, the coronae of all the stars that we see, is still an ongoing problem. So exactly as you say, the photosphere, the visible surface of the sun, that area of the sun is about 5,800, 6,000 degrees centigrade Celsius, roughly. Not precise, but it's high density. So that's essentially the final surface you can see before light gets scattered. So the analogy I often use here is like looking at a fog bank. A fog bank is not solid, but when you're on a foggy or a misty day, people measure the distance that you can see. And the denser the fog is, the shorter that distance is. Of course, you're looking at particles, and essentially the photosphere of the sun is the last surface at which your average photon of light would hit a particle and be scattered. So once it reaches this point, it can escape space, and so that gives us this illusion of a solid surface, when in fact you're just getting to a denser piece of gas. So the gas in the photosphere is quite dense, and a huge amount of radiation comes out from it. So when people look at the sun in the sky, and there's always the usual caveat here of please don't do that, because it's a very good way of damaging your eyes permanently. Yeah. But when you see the sun, when you see a photograph of the sun, that surface you're seeing is because there's a high density, so there's a huge amount of radiation coming out of it. When we get in a total eclipse of the sun, we suddenly see this beautiful diaphanous, very variable area around the sun we call the corona. And that's a much whiter, bluer light when you get color photos, which is indicative of a much higher temperature. And you think, well, it's a higher temperature. The amount of energy that you get from a photon is related to the temperature to the power 4, really incredible more energy. So shouldn't the corona be brighter than the surface of the sun? Why don't we see it? And the answer is because the individual photons are much more energetic, but there's far, 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 far less gas there. So there's much less flux. You've got higher energy photons, but a lot less of them, so you can only see it when the sun's blocked out. But the corona is incredibly hot. It's like 1 million, 2 million degrees. This incredibly tenuous gas, hot enough that the individual atoms, the individual nuclei are traveling quick enough that they'll escape the sun's gravity and flood out into the space. So corona links in with the solar wind. They're connected. And it's been an outstanding, really long-term question of how on earth the corona is heated to those temperatures. What on earth's going on? Now, the gravity idea, the idea of friction, there will be a little bit of friction. So any particles entering into the corona that are colliding with things will transfer energy to the atoms and nuclei that they're impacting. And you can get some degree of frictional heating there, but that's going to be a very, very, very small amount. It's not going to be anywhere near enough to do this, but you're right, it will probably contribute a bit of energy to this. And we know full well that there is continually dust and material falling into the sun. The most spectacular example of that are the sun-grazing comets that go in and fall apart and fragment, dumping a huge amount of dust and gas into that corona in a localized event. Now, the thing that to me, from a science education background, from the way I've been trained to think about problems, to say that Clint's idea doesn't quite work would be to look at the distribution of temperature in the corona. So the bulk of the mass entering into the corona would be the rarer events, like the breakup of a sun-grazing comet. You get a 100-meter-sized object breaking into dust, and that would inject a lot of material in one particular place. Yeah. So if the mechanism Clint was suggesting was the main one, you'd expect that one bit of the corona to then become much hotter and much brighter than the rest. And we don't observe that. So that to me is a very big telltale that it's not infalling material heating it up, because infalling material will be episodic and localized. And so you get one bit of the corona bright, then another bit, then another bit. And instead, the corona seems to be uniformly hot. Its shape and structure changes, though, through the solar cycle, and that's tied to the magnetic fields. And that seems to be a hint at what's actually going on. Now, it's absolutely right. We don't know the final answer, but I've been looking around, and there was a bit of work came out back in 2023, I think it was, that has come up with a potential part of the answer. So the answer here is linked to what researchers have called low-amplitude, decayless kink oscillations.
Right.
Again, we're really good at naming things. LADCOs, I guess, if you really wanted an acronym there. So the corona is tied in with the magnetic field of the sun. And as the solar cycle goes on, the magnetic field gets more and more tangled up, and you get loops and kinks happening near the surface of the sun, often tied with sunspots. And this is all tied in with flares and coronal mass ejections, things like this. What this is saying, I think, is that you get oscillations in those magnetic field lines, and the oscillations carry energy from the surface into the corona and can deposit it there. Now, normally those oscillations would be short-lived, so you'd only have a short period of time to deposit energy, so they wouldn't be very efficient. But these studies, these observations, found a kind of oscillation on those magnetic field lines that is of low frequency, so not carrying much energy per second, but can be long-lived because they are decayless. They're not decaying, so you get these oscillations that set up that keep going for minutes or hours. And that gives them a long time to put energy into the corona. So the authors of this work are talking about the fact that such oscillations, which seem to be really common from their observations, could act to deposit a large amount of energy in the corona. So it's a way of transferring energy from the magnetic field of the sun into the corona, which then carries that energy away into space, which ties into what we were talking about before, actually, in the gyrochronology, because it's that energy that is being lost that is transferring angular momentum away into space as well and causing the sun to slow down. So it is all linked together. Now, that study used data from European Space Agency's Solar Orbiter, NASA's Solar Dynamics Observatory, and they found one of these oscillations that lasted for 4 minutes. Now, 4 minutes doesn't sound long, but a kink, a wobble going on 4 minutes has a lot of time to deposit energy into space.
Yeah.
Read more about this. You can have a look online. It was published, I think, September 12, 2023 in Nature Communications, with the lead author being, and apologies for the pronunciation there, it's a solar physicist at the University of Warwick in the UK, and it's Valery Nakariakov, Nakariakov. You can find the findings online in Nature Communications. Their paper will do an infinitely better job of explaining what's going on than I just did, because they're the experts. But that seems to be the latest entry in our attempts to answer the question of WTF, essentially. What on earth is going on with the corona? How does it work? And that's how science progresses. You know, we don't know all the answers yet, and that's why this is such a fabulous question. And what Clint has done in coming up with a potential hypothesis for what happens is how scientists actually work. So we do just what Clint did. We come up with an idea. This, I think, is something that could contribute. This is how it could work. And then what happens is that we make predictions from that, which is how I extrapolated it, which is that if it's linked to infalling material and that's the main driver, what would we see? Well, we'd see the places where you get a big infall of material, you get a bright outburst of energy, and they would dominate, and we don't see that. So that theory doesn't work. We make testable predictions and test them. And this is just another step in the way to working to that answer. So I think it's a wonderful question. It is approaching something that we don't have all the answers for yet, but hopefully my answer helps a little bit in understanding just what's going on and what isn't happening.
Yeah, it also shows how complex these things are. I mean, the sun is the most studied star in the universe, as far as we're concerned, and we still haven't figured it out.
No,
so, and there's so many different kinds of stars, and they might not all be doing the same thing. So, yeah, there's much to learn. Clint, great question. Thanks for sending it in. This is Space Nuts. Andrew Dunkley here with Professor Jonti Horner.
3, 2, 1.
Space Nuts.
Jonti, our next question comes from one of our younger audience members, and I will hand it over to Sandy and Emily.
G'day, friend Andrew. It's Sandy here from Melbourne again. Thank you for answering my last question. That gag about the asteroids, pretty funny. Now, today, my 4-year-old daughter Emily wants to ask a question. So I'm going to pass it on to her.
How do we go to the moon?
Good job, Emmy. Thank you. Thank you for it, Andrew. Hopefully you can answer this question for us. Cheers.
Well, it won't be Fred nor Andrew. It will be Jonti. And hi, Emily. And Sandy's one of our regular contributors, but great to hear from Emily. A giant ladder? Probably not.
Probably not. It's an awesome question and a really good one, Emily. So thank you very much for that. It's difficult, is the very short thing. So traveling into space is challenging. And this is why we never managed it until 1957 when they launched Sputnik 1, which was the first thing that went into orbit around the Earth. The moon's further away. The moon, on average, is about 384,000 kilometers away. And what that means is if you want to get there in a reasonable amount of time, you need to travel really, really quickly. If you were to travel on the highway, you're going at 100 kilometers an hour, it would take you something like 3,800 hours to drive there, driving at that speed. And I think we've all got better things to do than that. So obviously we can't drive to the moon even if we had a road or we had a ladder. What we need to do instead is find a way to go very, very quickly and then travel there more rapidly. And to put that in perspective, when the first people walked on the moon back in the late 1960s, it took them about 3 days to get there. So they were traveling a lot quicker than you go when you're driving to school or driving to work.
Unless you've got P plates on your car. Then
Yes, even with the P plates, it's a push. I mean, I wish I could do my commute at this kind of speed because it would make life a lot easier.
yes.
So there's a few problems with that. You've got to get to a very high speed, which our cars just can't do. But you don't want to just get to that speed instantaneously because the acceleration would be really, really violent and really, really painful. And you feel this when you feel, somebody driving, maybe Sandy's driving, Emily, and they accelerate from the traffic lights. The harder they accelerate, the more you're pushed back into your seat. And so the more you're changing speed, the more you feel that. And this is something fighter pilots need to train to practice with, because when a fighter jet does a really sharp turn, the pilot can pass out because the G-forces are so extreme that all the blood is pushed out of their brain and they kind of fall asleep, and that's not good. So they have special clothes to deal with this. So what that means is we can't accelerate too quickly instantaneously because that would be bad for the people going. In addition, we've got to get out of the atmosphere, and the faster you travel through the Earth's air, the air pushes back at you, so it's really hard to speed up. And you can see this if you get a sheet of paper in your hand and try and push it through the air face onto the air. If you go gently, it's not too bad. But the harder you push it, the more the paper will bend back against your hand as it's pushed back by the air resistance. So a big part of getting to space is actually getting out of the Earth's atmosphere. And the way we solved all of these problems is to build really, really, really big rockets with multiple stages and use those to propel objects into space. And then when the first stage is dealt with, it falls away, you get rid of that mass and you get a smaller and smaller spacecraft. So when astronauts went to the moon in the 1960s, they had this enormous rocket called the Saturn V rocket. And you can look at pictures of it. When I was a kid, we went to Florida and I stood next to the Saturn V rocket. And it's bonkersly big. It's ridiculous.
Gosh, it looks big on TV, but when you're standing next to it, you go, oh my gosh, it is so much bigger than you think it's going to be.
Yeah, it's long enough that an Olympic sprinter would take about 10 seconds to run the length of it, something like that. It's ridiculously big. So that is the giant firework that we built to send astronauts to the moon. And it launches, the rocket engine goes off like a firework, pushing them higher and higher into the sky, speeding up at an acceleration that anything in the top could manage. So it's uncomfortable and you're being pushed back into your seats, but it's not so extreme it makes you unwell. And that big rocket is made of multiple parts. So when you get quite high up in the atmosphere and all the fuel is used up in the first part, that falls away and you've now got a smaller rocket that does the next burn and pushes you even faster and faster. And eventually you get out of the atmosphere, and that's good because you no longer have the wind resistance against you. And you can therefore use less energy to move around because you're not pushing against the wind. So once you're out of the atmosphere, it gets easier. What tends to happen then is that the rocket will do one final boost to get you to a speed where you'll travel towards the moon, and it will take you 2 or 3 days to get there, and you coast. You then go into free fall, floating there, just cruising along. This is a bit like when you've got up to speed on the highway and your car's just going along at the speed limit, minding its own business.
Put it in neutral and then just
Put it on neutral and you just cruise along. And at this point, you've got a couple of days of the astronauts feeling weightless because they're moving at the same speed as the spacecraft around them. And they just coast along. And then when you get near to the moon, you're going too quickly to orbit the moon because you're going at the speed you need to do to get there. So you need to turn around and slow down again to slow down enough to get into orbit around the moon. And so the rockets burn again, pushing you in the other direction, slowing you down until you're moving on an orbit around the moon that's kind of circular and maybe a few tens of kilometers above the moon's surface. And you sit there for a while and check that everything's okay because it's hard work and you want to make sure things are right. But then when the astronauts went to the moon, the final part was that 2 of the astronauts on the mission climbed into this small landing module. And the third one stayed piloting the orbiter. They stayed above the moon and didn't go down to the surface. But the landing module separated from the orbiter, got nudged away, and then used its own small little rockets to boost and slow down and boost and slow down until it touched down and landed safely at a specific point on the moon. And the pilot had to watch up what they were doing. They were kind of looking out at the ground below to pick the best place to land. And with the very first landing, when Neil Armstrong and Buzz Aldrin landed on the moon, they kept going and nearly ran out of fuel. They only had a few seconds left before they would have to abort and boost back up. Because when you land on the moon, you've got to get back. So they land on the moon, they do all their fun things, they bounce around like kangaroos. But then to get back to Earth, they've got to get back in this small landing module, which is probably not got much more room in it, to be honest, than the interior of your car, strap themselves in, and then the top of the module detaches, leaving the legs behind, and the rocket pushes them back up so they can get into orbit around the moon. They dock and reconnect with the parent spacecraft that the pilot was sat in waiting for a couple of days on their own. Then they turn on their rockets and they come back to the Earth. Same thing, they boost up to a high speed, then they cruise along, floating there for a couple of days until they get near the Earth. Then they boost their rockets again to slow down, fall into the atmosphere, and land again. So it's a big, long, dramatic journey. Now, we've got better technology now, so we can do it more effectively, and that's why NASA are hoping to send people back to the moon in the next few years. Now, everybody who went to the moon so far, all 12 people who walked on the moon were people who looked a bit like me and Andrew and Fred. They were older white men, and that was it.
That was it.
And, you know, these were all people who trained as test pilots and stuff like this. With the next people landing on the moon, they're going to be more, you know, a wider variety of people. So the hope is that in a few years' time, we'll see the first woman walk on the moon and the first person who isn't white to walk on the moon as well. And that'll be really good because it's important to know that this is something anybody can do. Everybody could learn to be an astronaut. It's very competitive and really hard. But if you only ever see people who look like me and Andrew do it, you'll think they're the only kind of people who can. So it's really important to have everybody represented in this. And I think it's really exciting that in a few years' time, we won't just talk about men walking on the moon, but we'll talk about men and women walking on the moon. That's going to be really cool.
Yes, it is. I grew up in the pioneering era of space flight and going to the moon. And I was quite young when Neil Armstrong put his foot on the surface and was followed by Buzz Aldrin. I was so very lucky to meet Buzz Aldrin many, many years later, and I got to interview him for the Australian Broadcasting Corporation. That was probably one of the highlights of my career, to be honest, to meet someone so famous, one of the most famous people in the world because of what he did. But it's reached a point now where people are going up and down all the time into space, and we'll never know their names because it's become so common. But as you say, with Artemis going back to the moon and those people setting foot on the surface again, men and women of multiple races, they will again reignite that fame that goes with doing something so extraordinary. And Emily, I would imagine that in your lifetime, it will reach a point where there will be people living on the moon. I expect that will happen. Might even happen in my lifetime, but certainly in yours, it'll be very different. Maybe even Mars, Emily. Thank you for the question. Thanks, Sandy. Always great to hear from our younger listeners. Jonti, I'm going to make an executive decision and I'm going to pigeonhole Fenton until next week because his question is 2 hours long
Yeah.
And I imagine the answer will be 5 times that. So I just don't think we can fit it in today. But it's a great question about the radiation of Jupiter. We will put that at the top of the tree for next week's Q&A episode. But thanks to everyone who contributed. And don't forget, if you've got questions for us, jump on our website, spacenutspodcast.com and spacenuts.io, our 2 URLs, and just click on that little AMA link at the top. That's where you send your text and audio questions. If you've got a device with a microphone, you're all set. And have a look around while you're there. And don't forget our social media, very, very active. The Space Nuts Facebook page is our official page, but we've got the Space Nuts Podcast Group Facebook page where people get together and chat and talk and compare photos and notes. And yeah, it's very, very active. It's a great site. And thanks to our administrators who look after it for us, because I haven't got time most of the time, except when I've got time. And it's time to go. Thank you very much, Jonti. Always great fun. We'll catch you next week.
Yeah, catch you later. Thank you for having me.
Jonti Horner, a professor of astrophysics at the University of Southern Queensland, joining us while Fred is away, and we'll speak to Jonti again next week. And to Hugh in the studio, he was AWOL because he's putting P-plates on his car so that he can go faster. And from me, Andrew Dunkley, thanks for your company. We'll catch you on the very next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.